godlike ownage.
What is up, ladies and gentlemen? Okay, we're gonna go full cam for this. Okay, should I make some tea? Should I drink it? Should I drink it a tea? Or should I drink some the, as the French say? Should I drink the? That is what they say, you know. I am a French connoisseur myself, but anyway, guys, what are we doing? What is the plan for today? So, yesterday we reviewed some math. Okay, we might recap some of what we did there. We might not, whatever. Today, though, I have a time limit. I gotta go somewhere at like 5 p.m. pretty much. I gotta be done with this. So we have like 4 to 5 hours, 4.5 hours to get through what we're gonna do. So my plans were to zoom through some YouTube lectures, and then probably look at some homeworks, but I don't know. I think it would probably be more useful to just look at homeworks and then figure out shit from there. That's what I think would be more useful. I'm not sure. So I have two options. I can either review quantum mechanics or I can review solid state physics. If I review solid state physics, I would have to be reading chapter 12, which I should probably do. Okay, let's look at the calendar. Let's look at which midterms are which. Okay, so Thursday, I technically have the whole day on Thursday to study. Should probably review some solid state, actually. Read through chapter 12, right? Crystal structure. It's a decently large chapter. So what is going to be on the exam for this? Ooh, chapters 12 to 13? No way. It's also chapter 13, bro? What the hell? Hold up. Wait a minute. Okay. Actually, I have to read chapter 12 and chapter 13, apparently. I did not know that. So, we're definitely going to be reading solid state physics. Because now I just found out I'm actually way more behind in the textbook than I had thought I would be originally. So, let's line these things up. And, here we go. I think this calls for a little tea break. So we have to learn crystal structure. How is chapter 13 on the freaking exam? We didn't have any homeworks pertaining to chapter 13, did we? What? Bro, isn't this something? I'll email this person. Figure out what is happening, what's going on. Okay, subject. Say physics 141A in square brackets, and then midterm 2, chapter 13, logistics. Day. This is Paul, student in physics 141A. I see that in the announcement posted on B courses, you mentioned that term 2 will cover chapters 5 through 7 and chapters 11 through 13. Don't worry, guys. We're writing important emails right now. Okay, this is all a part of the process. Okay, it's all a part of the process, ladies and gentlemen. Okay, this is the process. Okay, I'm gonna make some tea in the meantime. Multitasking. Okay, drop that in there. That's cooled down, right? Not enough. There. These. Henceforth, wherever thine heart's desire. Okay. Oh. My head hurts, dude. I should not have ran a 5K today. I need a drink. Water. I was wondering in what way would material from chapter 13 be incorporated into the midterm? Would we given that we haven't extensively, given that we haven't done specific problems from Chapter 13 for homework. Would we need to too many qualitative? Okay, I haven't read I haven't read chapter 13 yet, so I feel uncomfortable sending this email now. Thank you for any help. Best. Oh. Okay, so I haven't actually read the chapter yet. So I don't know if like we actually did cover it in a class or something. I haven't been going to lecture. I know it's bad of me to do, okay, but listen, I don't learn anything from the lecture. It's a big waste of time from my standpoint. I knew we were missing something. We were missing that spice of the 3DS music. Okay. My tea is done. I'm gonna go grab my tea, okay? Don't worry, Patriots. I will be back. You'll be able to see me the whole time. I'm running low on tea. I don't know how much tea I have left, okay? But I saw at the grocery store there was tea, and I said to him, I said, "Sir, this tea is very good. It's very good quality. It's very, very cheap, very nice." You know, I walked into the room, I saw a lot of green tea, and I said, "Wow, this is a lot of green tea." Okay, Trump impression over. I'm not very good at it anyway. I never claimed to be good at it. Okay, I just claim to be a citizen, a free man. Okay, I'm Gordon Freeman. Half-Life much? Whoa, Half-Life reference? Whoa. G-Man? Whoa, Skibbity? Whoa. Okay, guys, I'm not gonna lie, my head is hurting. I think fish oil will cure that. I think fish oil will cure the headache. I'm also going to close the window because a lot of sound leaks out actually. A lot more than I thought. So, fish oil. 2 pills. Okay. Tally-ho. Alright, so we need to read through chapter 12 and 13. That might take all of our time. I also need to watch lectures on quantum mechanics. How many videos do I need to watch? 1, 2, 3, 4, 5. What were all the topics that were covered until the midterm? The fuck? Syllabus. What was covered? It was all the way up until like time-independent perturbation theory, right? And then after midterm, we started learning like fine structure, everything like that. The Zeeman effect. Yeah. I should be focusing on math a lot more. I think tomorrow I'll be focusing a lot more on math. Definitely on Sunday. You know what? I have time. You know, guys, I've suddenly become a bloomer. I am now thinking to myself, wow, I have a lot of time. Also, remind me, don't lean back. Okay, I need to be upright and alert. Because from leaning back, last night my lower back hurt a lot when I was gonna go to sleep, so. Also, there's something in this room. I think this room is really stuffy, man. Ugh. Fucks with my nose. There has to be like a lot of dust, I think. Kind of. You can kind of do a sham test by like turning on the flashlight in your phone. Turning on the flashlight in the phone. And then just like pointing it in the air, and then you can see the dust particles, but it's not really a scientific method. But yeah. Jesus. Who are these people? Boy, person on SoundCloud just liked one of my songs, and in their profile they have a playlist titled Middle School, and the first track was 21 by something. And it's like, hey, I'm not judging, okay? I'm not judging. You know, some people might say the type of music you like is either like, or like, boom, bap, da, da, bap, or like, find your dreams come true, and I wonder if you know what it means to find your dreams come true. Bro, I don't want to read this shit, bro. Hold on. That's my negative. Sorry guys. That was my negative me speaking. Positive me. Positive Paul has now just unlocked his brain. Okay. I'm not positive. I can't wait to learn about crystal structure. This is such an important concept in solid state physics. I've heard crystal structures and lattices mentioned all the time, and I'm glad to actually see a geometrical and physical interpretation of all of this random stuff that we've been learning so far. Wow! I'm so much more positive as a person. Okay. Positivity. Over with. Okay. Okay, listen. Now listen up. Sorry guys, I'm just gonna update my finances real quick. I need to add to my spreadsheet that I had McDonald's for $7.72. Yeah, McDonald's $7.72. Wow, and look at that, I'm over budget for this month. To be fair though, I set a very stringent budget, like almost unrealistically stringent on myself. Of like spending like what, like $150 a month or something like that. So of course I'm over budget already, but yeah. $150 a month in this part of town, boy, that's like you get a cheeseburger and you're over budget. Oh, I clicked. Okay. All right, guys, time to become education mode. Education for free with Education Connection. Get connected for free with Education Connection. Righty tighty, lefty loosey. Turning it to the left, so I need to turn it this way. Okay, I think it's as tight as it can go. Whatever. Okay. It might also be the pop filter. I mean, honestly, the pop filter could be just like have dust and a bunch of particles in it, and me coming close to it just like messes me up. I might need to get... Do they have cleanable pop filters? Cleanable pop filter. Oh, you could rinse it.
A regular pop filter, always in your face, blocking your lyrics and never holding the position you want it to. It's time for a change. Isopop, your premium pop filter. Smaller and more effective than other pop filters. Easy to clean thanks to its cleanable Isopop infill. Optimized for reading your lyrics without getting in the way of your sight. No coloration. Sturdy and stays in place. And it fits perfectly inside your Isovox 2 without blocking your sight, thanks to the compact size. Isopop, your premium pop filter.
It just feels like a scam. How much is it? Is it like $80, dude? I swear to God. $130 for a pop filter? What the fuck, dude? It is not... Pop filters are not worth that much, dude. You're kidding me. Apparently there's an Isovox, a portable vocal booth.
I'm standing outside here, middle of Sweden. It's sunshine, we have some birds singing, it's windy, some jet skis riding on the water. And this is how it sounds like without the Isovox. 1, 2, 3, 4, 5. Oh, it's very quiet inside here. You can really get that dry sound even in an environment like this. Now I'm standing in a living room. Notice how reverberant it is here. It's really hard to get that dry pro sound. So as you can hear, the Isovox 2 completely eliminates the room echo. So I'm in the bathroom recording myself. Perfectly normal. But the room sound in here just don't work. So, if you ever need to record in your bathroom for...
Is this gonna cost like $500? $1,000 for a freaking... Guys, I can't make this up. I cannot make this up. I can't make this up. $1,000 for this. For a box that you put over your head and you talk into.
Get that dry pro sound. So as you can hear, the Isovox 2 completely eliminates...
And this is just to get that stupid sound where it's like, my voice is super deep and I'm like an audiobook. What the fuck? Okay, 786, you know what, actually not bad. Wait. No, 786 is still bad. That was just marketing that worked in real time. This is the Isovox Go. What the fuck is the difference? Isovox Go? An RF shield. What is this? We're doing a lot of Googling today. RF shield for audio? Damn. I don't know, man. This is just crazy. It's just crazy. It's a lot of money. It's a lot of money. For a box that you could build yourself, dude. You can fucking build it with like probably towels and cardboard. Okay, guys, we spent like 30 minutes procrastinating. Okay, now I only have definitely 4 hours. Actually, no, I have like 3 hours. Okay, whatever. Let's just read it. Having introduced a number of important ideas in one dimension, we must now deal with the fact that our world is actually spatially three-dimensional. No, we have to deal with the three-dimensional space? While this adds a bit of complication, really the important concepts are no harder in 3 dimensions than they were in 1 dimension. Some of the most important ideas we have already met in 1 dimension, but we will introduce them more generally here. There are 2 things that might be difficult here. First, we do need to wrestle with a bit of geometry. Hopefully most will not find this too hard. Secondly, we will also need to establish a language in order to describe structures in 2 and 3 dimensions intelligently. As such, much of this chapter is just a list of definitions to be learned, but unfortunately this is necessary in order to be able to continue further at this point. Lattice and unit cells. A lattice is an infinite set of points defined by integer sums of a set of linearly independent primitive lattice vectors. Okay. For example, in 2 dimensions, as shown in figure 12.1, the lattice points are described as R, N1, N2. Male. What mail am I getting? Oh wow, something useless. Very glad. The lattice points are described as R, N1, N2 equals N1, A1 plus N2, A2, with A1 and A2 being the primitive lattice vectors and N1, N2 being integers. In 3 dimensions, points of a lattice are analogously indexed by 3 integers. Boom, boom, boom. Yep. Makes sense. Okay, I guess this makes sense. 1, 2 is equal to 1a plus 2a2. Note that in 1 dimension, this definition of a lattice fits sort of the previous description of a lattice as being the points r equals na. Yeah, that's true. With na being the integer. With n being the integer. And a being our, like, unit or whatever. Or unit cell. Okay. It is important to point out that in 2 and 3 dimensions, the choice of primitive lattice vectors is not unique. As shown in figure 12.2, in 1 dimension, the single primitive lattice vector is unique up to the sign or direction of A. Okay, sure. It turns out that there are several definitions that are entirely equivalent to the one we have just given. Equivalent definition 12.1.1. Dude, my nose is fucked up. I really wonder if it's something to do with this goddamn pop filter. Yeah, the microphone is kind of dusty. Do I really need to clean this stuff off regularly? Whatever. Yeah. Okay, I'm gonna raw dog the microphone here. I'm raw dogging it. I'm just gonna talk directly into it, okay? Or I guess I'll have it here. I don't know if it'll still affect the sound, actually. Pop, pop, pop. Does this affect the sound? I don't know if it'll still affect the sound, actually. Pop, pop, pop. Does it? Okay, it kind of did there. Well, it did actually a lot there. And now we'll talk with this. Pop, pop, pop. Does it affect it? Actually a lot there. And now we'll talk with this. Pop, pop, pop. Does it affect it? Okay, the pop filter actually does affect it. But you know what? This isn't an audiobook. Okay, this is not an audiobook of this book. Okay, if you want it, go read it yourself. Turns out that there are several definitions that are entirely equivalent to the one we've just given. Oh my god, my nose, dude. What the freak? Oh. Yeah, I gotta clean the pop filter. That's something I should do. Let's put that on my reminders. Clean pop filter and mic of dust. Okay. Okay. A lattice is an infinite set of vectors where addition of any 2 vectors in the set gives a third vector in the set. So a very broad definition. It's an infinite set of vectors where addition of any two vectors in the set gives a third vector in the set, okay? It is easy to see that our definition 12.1 implies the second one 12.11. How is that true? Lattice is an infinite set of points defined by an integer sum of linearly independent primitive lattice vectors. Okay. Yeah, it does. An infinite set of vectors where addition of any two vectors in the set gives a third vector in the set. Sure. A less crisply defined, but sometimes more useful. A lattice is a set of points where the environment of any given point is equivalent to the environment of any other point. Okay, that makes sense. Yeah, that does sound a little bit more useful. It's kind of funny just having the pop filter over here. I'll extend it a little bit more. Just so it's kind of, you know what? Screw it. It'll say hi. Well, hello. What's up? Pop filter here. Okay. It turns out that any periodic structure can be expressed as a lattice of repeating motifs. A cartoon of this statement is shown in figure 12.3. One should be cautious, however, that not all periodic arrangements of points are lattices. The honeycomb shown in figure 12.4 is not a lattice. This is obvious from the third definition, 12.1.2. The environment of point P and point R are actually different. Point P has a neighbor directly above it. The point R, whereas point R has no neighbor directly above. Okay, yeah. In order to describe a honeycomb or other more complicated arrangements of points, we have the idea of a unit cell, which we have met before in section 10.1. Generally, we have a unit cell in a region is a region of space such that when many identical units are stacked together, it tiles, completely fills all of the space, and reconstructs the full structure. What? A region of space such that when many identical units are stacked together, it tiles all of the space and reconstructs the full structure. I know what you're trying to say is that if you have something, when you tile it, it'll just recreate that something, but on a larger scale. A unit cell is a repeated motif, which is the elementary building block of the periodic structure. Yeah. To be more specific, we frequently want to work with the smallest possible unit cell. So a primitive unit cell for a periodic crystal is a unit cell containing exactly one lattice point. Okay. As mentioned in section 10.1, the definition of the unit cell is never unique. This is shown, for example, in figure 12.5. Sometimes it is useful to define a unit cell which is not primitive in order to make it simpler to work with. This is known as a conventional unit cell. Almost always these conventional unit cells are chosen so as to have orthogonal axes. Okay. It just popped into my mind that I should probably read through chapter 5 through 7 again. Periodic table, chemical bonding, types of matter. How long are these chapters? Holy shit. Okay, at least chapter 7 is kind of short, but holy fuck. Chapter 5 is pretty short. Chapter 6 is not short. And then chapter 7. Okay. Let's start making a list of things I should review for 104. I mean, 141A. 141A. So I should read chapters 5 through 7 just to understand it. I'm reading through chapters 12 and 13 now. Review all homeworks. Review all the homeworks. What else? Review discussion notes. Probably. That would just be good. And then do practice midterm. I feel like when I have like the bare microphone, like I'm talking too loud. I feel like it's just too loud. Is it? Actually, it's just too loud. Is it? Actually, it's just too loud. No, it's not that loud. Yeah. Okay. Going back to what we were reading. Primitive unit cell. Okay, so far we have what? A lattice, which is just an infinite set of points. Okay. We have a unit cell, which is like the smallest repeated thing. The primitive unit cell contains just one lattice point. Okay. You know, not having a pop filter actually makes the face cam a lot better. So I'll have to decide whether or not it's worth it to have a pop filter. Because I mean, with it blocks my entire face, you know? But anyway. Sometimes it is useful to define a unit cell which is not primitive in order to make it simpler to work with. This is known as a conventional unit cell. Almost always these conventional unit cells are chosen so as to have orthogonal axes. Some examples of possible unit cells are shown for the triangle lattice in figure 12.6. Wow, thanks for having it all the way down here. Conventional unit cell, primitive unit cell with only one lattice point. This technically does not have one lattice point. Wigner-Seitz unit cell. Okay. Which is often easier to work with than axes which are non-orthogonal. Okay, yeah. A note about counting the number of lattice points in the unit cell. It is frequently the case that we will work with unit cells where the lattice points live at the corners or edges of the cells. When a lattice point is on the boundary of the unit cell, it should only be counted fractionally depending on what fraction of the point is actually in the cell. So for example, in the conventional unit cell shown in 12.6, there are 2 lattice points within the cell. There's 1 point in the center, then 4 points at the corners, each of which is 1/4 inside the cell. So we obtain 2 is equal to 1 plus 4 over 1 over 4 points in the cell. Since there are 2 lattice points in the cell, it is by definition not primitive. So each of these are halfway. I guess the point is 1/4 in. So you have 1 plus 4 times 1/4 is 2 points. Okay. This is a stupid way to construct it. You should put 1 plus 4 times 1/4. So you obtain 1 plus 4 times 1/4 equals 2 points in the cell. Since there are 2 lattice points in the cell, it is by definition not primitive. Yep. Yeah, I guess we do just have 1/4 of the points in there. Thought we would count the distance, but sure. Okay. Oh. Oh, guys, I'm getting a little bit sleepy. Guys, I am not going to lie, I'm getting a little bit sleepy, but that's okay. Okay, what was I reading? Yeah. Similarly, for the primitive cell shown in figure 12.6, the 2 lattice points at the far left and far right have a 60-degree slice, which is 1/6 of a circle inside the cell. The other 2 lattice points each have 1/3 of the lattice point inside the unit cell. Thus, this unit cell contains 2 times 1/3 plus 2 times 1/6 equals 1 point and is thus primitive. Okay, yeah. Okay, so they did it correctly here. Contains 1 point. Contains 4 in a... Like, oh my god. How do you make mistakes like this, man? Note, however, that we can just imagine shifting the unit cell a tiny amount in almost any direction such that a single lattice point is completely inside the unit cell and the others are completely outside the unit cell. This sometimes makes counting much easier. Yeah. Given a lattice point, the set of all points in space which are closer to that given lattice point than to any other lattice point constitute the Wigner-Seitz cell of the given lattice point. There is a rather simple scheme for constructing such a Wigner-Seitz cell. Choose a lattice point and draw lines to all of its possible near neighbors, not just its nearest neighbors. Then draw perpendicular bisectors of all these lines. The perpendicular bisectors around the Wigner-Seitz cell. It is always true, bound the Wigner-Seitz cell. It is always true that construction for a lattice gives a primitive unit cell. In figure 12.7, we show another example of the construction for a two-dimensional lattice. You draw straight lines, and then you draw a perpendicular bisector of those lines. Okay, makes sense. Yeah, you draw straight lines, perpendicular bisector. Okay. Okay. Interesting footnote, but okay. All right, a similar construction can be performed in 3 dimensions, in which case one must construct a perpendicular bisecting planes to bound the Wigner-Seitz cell. See, for example, figures 12.13 and 12.16. Why is it all the way down here? Yeah. You draw a line to that, and then you have a plane. So the line from here to this one, and you do a plane halfway. Okay. Okay. Oh. Guys, I don't know how you do it. I don't know how you guys can do it nowadays. Okay. I'm distracted. I'm too distracted nowadays, man. I'm looking back and forth at everything. Okay. Okay. The description of objects in the unit cell with respect to the reference lattice point in the unit cell is known as a basis. This is the same definition for basis of used in section 10.1. In other words, we think of reconstructing the entire crystal by associating with each lattice point a basis of atoms. In figure 12.8, we show a periodic structure in 2 dimension made of 2 types of atoms. On the bottom, we show a primitive unit cell with the position of the atoms. Okay, so on the top, we show a periodic structure in 2 dimension made of 2 types of atoms. On the bottom, we show a primitive unit cell expanded with the position of the atoms given with respect to the reference point of the unit cell, which is taken to be the lower left-hand corner. Okay, so you take this as a unit cell, and thus this is in the middle. Yeah, that's 1/4, that's 3/4. Yeah, man. Yeah, dude. Uh, Large light gray atom. Yep. R N1 N2 A N1 A N2 A N1 X hat A N2 Y hat. R like great A N1 A2. These plus A over 2 A over 2. N1 N2 plus A over 4 A over 4 A over 4 3A over 4 3A over 4 A over 4 3A over 4 3A over 4. Yep. In this way you can see that the positions of these atoms in the crystal are the lattice plus the basis. We now return to the case of the honeycomb shown in figure 12.4. The same honeycomb is shown in figure 12.9 with the lattice and the basis explicitly shown. Here are the reference points. The small black dots form a triangular lattice where we could write the primitive lattice vectors as A1 equal to X, A2 is equal to A1 half X plus A3 over 2Y. That's such like a weird thing to make it like this. Wait, what? I feel like these have to be flipped, right? A1 has to be here because this is the X hat, unless you're defining this as the X hat, which is doing kind of weird. Okay, I'll take you know what, I'll take it. I'll take your word for it. Okay. I get this makes sense, but this is kind of weird. Like this is usually the X, whatever. Dude, I'm really tired. What the fuck? I'm like fighting to stay awake. Come on, dude. I only got one more chapter after this, and then I'm done with chapter 12, and then it's on to chapter 13. Okay, the simplest lattice in 3 dimensions is a simple cubic lattice shown in figure 12.10. The primitive unit cell in this case can most conveniently be taken to be a single cube, which includes 1/8 of each of its 8 corners. Only slightly more complicated than the simple cubic lattice are the tetragonal and orthorhombic. So tetragonal and orthorhombic lattices, where the axes remain perpendicular, but the primitive lattice vectors may be of different lengths. The orthorhombic unit cell has 3 different lengths of its perpendicular primitive lattice vectors, whereas the tetragonal unit cell has 2 lengths, the same and 1 different. Orthorhombic A, B, and C are all different. With this tetragonal, this is a bad illustration. This should be further. This should be a little bit further. Just a bit. So you can really show that these are different, but whatever. Yeah, the cubic one is wrong anyway. Whatever, dude. I'm not an artist. Okay. Dude, I gotta take a power nap, bro. Oh my god, I can't do this. Okay, so we just went over lattices here. We have to go over lattices in 3 dimensions. Pretty sure this is all standard stuff anyway. Okay, I'm gonna go take a quick power nap. Okay, 10 minutes. I'll be back. For now, listen to that, okay? I'll be right back. 10 minutes. 10 minutes, I swear to God, I'm not gonna go for a power nap and then, leave you to dust for an hour. Ten minutes. You know how I know? Hey Siri, set a timer for 15 minutes.
15 minutes?
I know, 15 minutes, but by the time I get into bed and take a nap, it's gonna be 10 minutes, right? Alright, I'll be back. Guess what, ladies and germs, I'm back. Okay. Listen, it was a little bit longer than I said. Okay, it was a little bit longer, but... However, consider this. Okay? As I was first dozing off into sleep, I had like a vision of like a really cool movie idea. And then when I told the phone to take a note of it, I suddenly realized how lame it was as I was saying it out loud. And I was like, what the fuck? This is so stupid. But yeah, that was like pretty much like as I was trying to fall asleep, so I had to reset the timer. Anyway, listen. Listen. I know I was a little bit more gone for 10 minutes, okay? But I think I'm good now. Okay. So let's start reading. Lattices in 3 dimensions. Dude, I'm so like, my hands and my feet are like super warm. I think that's because I went running today. It's just causing my whole body to heat up. Okay. The simplest lattice in 3 dimensions is a simple cubic lattice shown. Sometimes called a P, blah, blah, blah. Yeah, we already talked about that. Okay, next page. I don't think are we dealing with 3-dimensional lattices? Yes, we are. Okay, we might as well just fucking read this. Conventionally, to represent a given vector amongst the infinite number of possible lattice vectors in a lattice, one writes UVW equals UA1 plus VA2 plus WA3, where UV and W are integers for cases where the lattice vectors... Bong bong, someone's bonging outside. For cases where the lattice vectors are orthogonal... Bro. You guys probably can't hear that. Anyway, for cases where the lattice vectors are orthogonal, I'm still tired. I'm really tired today. Isn't that fucked up? Ain't that a bitch? I should also charge my phone with this cable. This one. No. I almost dunked it in cold tea. It's a cold brew. Sir, you served my coffee cold. It's a cold brew. Don't argue with me. Sir, I asked for a fresh, hot, medium roast coffee 3 minutes ago, and you gave me, within the span of 3 minutes, you gave me a perfectly cold cup of coffee. How long has this been sitting on the counter? Do not question me. I'm the barista, okay? I'm the barista, okay? Do not question me. I'm the barista. What am I doing? Okay. Guys, I can't focus. I'm really tired. I should not have run a 5K in the morning. That actually was not a good idea. No, it's not that. You know why I'm tired? It's because I ate fucking McDonald's. I ate a 20-piece nuggets and 2 medium fries. And I thought that wouldn't send me crashing. Okay, that has me crashing now, but you know, whatever. I'm crashing and burning now, but it's okay. Okay. For cases where the lattice vectors are orthogonal, the basis vectors a1, a2, and a3 are assumed to be in the x, y, and z directions. We've seen this notation before, for example in the subscripts of the equations after definition 12.1. Lattices in 3 dimensions are also exist where axes are not orthogonal. We will not cover all of these more complicated lattices in detail in this book. The principles we learned in the more simple cases generalize fairly easily and just add further geometric and algebraic complexity without eliminating the physics much further. 2 particular lattices with orthogonal axes, which we will cover in some detail, are body-centered cubic BCC lattices and face-centered cubic FCC lattices. Okay, interesting. body-centered cubic... Okay. The body-centered cubic lattice... The body-centered cubic lattice is a simple cubic lattice where there's an additional lattice point in the very center of the cube. It is sometimes known as cubic eye. Okay. The body-centered cubic BCC lattice is a simple cubic lattice where there is an additional lattice point in the very center of the cube. It is sometimes known as cubic eye. Okay. The fuck is a plan view? They have not mentioned plan views at all, dude. What is a plan view? Oh, right. It's described right here. The unit cell is shown in the left. Another way to show this unit cell, which does not rely on showing a three-dimensional picture, is to use a so-called plan view of the unit cell, shown in the right. A plan view is a two-dimensional projection from the top of an object where heights are labeled to show the third dimension. In the picture of the BCC cell, there are 8 lattice points on the corners of the cell, each of which is 1/8 inside of the conventional unit cell and 1 point in the center of the cell. Thus, the conventional unit cell contains exactly 2, 8 times 1/8 plus 1 lattice points. Yes. This is not the principal unit cell. Primitive unit cell is a conventional. Packing together these unit cells to fill a space, we see that the lattice points of a full BCC lattice can be described as being points having coordinates x, y, z, where either all 3 coordinates are integers times the lattice constant a, or all 3 are half odd integers times the lattice constant a. It is often convenient to think of the BCC lattice as a simple cubic lattice with a basis of 2 atoms per conventional cell. The simple cubic lattice contains points x, y, z, where all 3 coordinates are integers in units of the lattice constant. Within the conventional simple cubic unit cell, we put 1 point at position 0, 0, 0, and another point at the position 1/2, 1/2, 1/2 in units of the lattice constant. Thus, the points of the BCC lattice are written in units of the lattice constant as r corner, n1, n2, n3, r center, and 1, n2, n3 plus 1/2, 1/2, 1/2. Okay. 1 point at position 0. So we put the corners are 0. The center is 1/2. As if the 2 different types of points were 2 different types of atoms. Although all points in this lattice should be considered equivalent, they only look inequivalent because we have chosen a conventional unit cell with 2 lattice points in it. From this representation, we see that we can also think of the BCC lattice as being 2 interpenetrating simple cubic lattices displaced from each other by a half, half, half. We may ask why it is a set of points for R. In terms of our first definition of a lattice, we can write the primitive lattice vectors of the BCC lattice as A1, uh-oh. Do you know what that is? Let's be real. No freaking way. Dude, my hands are like so sweaty today. What is going on? Okay. It is easy to check that any combination gives a point within our definition of the BCC lattice, that the three coordinates are either all integers or all half-odd integers times the lattice constant. Further, one can check that any point satisfying the conditions for the BCC lattice can be written in the form of equation 12.5. I don't really get this. Let's just Google it. Oh.
In this video, I'm going to give you a basic introduction into unit cells. Now, there's three structures you need to be familiar with. The first one on the left is the simple cubic structure. The second one in the middle is the body. The square root of 3 times the edge length x is equal to the length.
Let us consider a body. We arrive at a point. Finally, the interaxial angle between A. So the volume of belongs to the country. You have to pay. There are infinite. Let us consider a body-centered cubic lattice. This lattice is generated by a conventional unit cell as shown here. This unit cell has lattice points at the corners as well as one at the body center. But note that when we say BCC lattice, we mean the points generated by the repetition of this unit cell and not the unit cell itself. For a given lattice, there are infinitely many unit cells. The conventional unit cell is only one of them. In the case of BCC, this conventional unit cell is a non-primitive one because it has an additional lattice point in the center apart from those at the corners. In a primitive unit cell, the lattice points are located only at the corners. For some application, for example in the determination of reciprocal lattice, it is useful to work with a primitive unit cell. Again, there are infinitely many primitive unit cells possible for a given lattice. In this video, we describe one such primitive cell associated with BCC lattice. Let us select our first primitive basis vector, the vector from center to one of the corners, from the center to one of these corners. We call it A1. Similarly, we select our vectors A2 and A3 again from center to these corners. These three primitive basis vectors span a primitive unit cell for the BCC lattice. Let me try to show you this by completing the unit cell. You have to pay particular attention as we have to use 3 points outside this unit cell. Let me add vectors A1 and A2. A1 and A2. You get to a point which is the body center of a unit cell which is on the top of the given cube. At this point, I have not drawn the full cube on the top, but you can imagine that there is a cube sitting on the top face of this cube and this point is the center of that cube. You can convince yourself. Similarly, by adding A2 and A3, we come to a point which is at the body center of a unit cell in the front of the given cube. And finally, adding A3 and A1, we arrive at a point which is at the body center of a unit cell to the right of the given cube. You can now see three parallelograms. Meeting at the body center. These are the 3 faces of the primitive unit cell. Also, we have 7 points of the primitive unit cell. One is the body center point, and then 3 corners of the original cube, and then 3 body centers of the cube adjacent to this given cube. So 7 points. You know that a parallelepiped unit cell consists of 8 points, just like the original cube. So one more point is required to complete this unit cell, and that is this corner of the cube. If we now connect this point, we get a complete picture of the primitive unit cell. It is useful to express the primitive basis vectors A1, A2, and A3 in terms of the orthogonal basis vectors E1, E2, and E3 shown in green here. These are unit vectors along the edges of the original cube. So I want to express A1 in terms of E1, E2 and E3. To do this, let me start at the tail of the A1 vector, which is the body center, and take a step A by 2 in minus E1 direction. E1 is this edge. I am starting from here and taking a step A by 2 in the minus E1 direction. You can convince yourself that you will reach the center of the back face. Then I take a step A by 2 along E2, and that will bring me to the middle of this vertical edge. And finally, we take a step A by 2 in the E3 direction to arrive. I can also write it as A by 2 times minus E1 plus E2 plus E3. Similarly, we can write A2 as A by 2 E1 minus E2 plus E3, and A3 as A by 2 E1 plus E2 minus E3. Note the convention we are using here. If we travel in the negative E1 direction, I am labeling that vector as A1. If we travel in the negative E2 direction, I am labeling that vector as A2, and if we move in the negative E3 direction, the vector is called A3. Note that the three vectors A1, A2 and A3, A1, A2 and A3 are all of equal length and equal to these vectors, alpha, beta and gamma, the interaxial angle between A1 and A2 0.5 degrees. A1 dot A2.
I didn't know this. You take the determinant, and if it's non-zero, then it shows linear independence. I did not know that. Okay. Oh, now I get it. See, it's a good thing I didn't send that email at the start, because this is dealing with the real lattice space, and then going into the reciprocal lattice space is what we dealt with in actually a discussion. So, yeah. The coordination number of a lattice. Wait. We can also check that our description of a BCC lattice satisfies our second description of a lattice, that addition of any 2 points of the lattice gives another point of the lattice. More qualitatively, we can consider definition 12.1.2 of the lattice, that the local environment of every point in the lattice should be the same. Examining the point in the center of the unit cell, we can see that it has precisely 8 nearest neighbors in each of the possible diagonal directions. Similarly, any of the points in the corners of the unit cells will have 8 nearest neighbors corresponding to the points in the center of the 8 adjacent unit cells. Dude, my hands are so sweaty. What is going on today? Think I ran too hard. The coordination number of a lattice, frequently called Z or Z, is the number of nearest neighbors any point of the lattice has. For the BCC lattice, the coordination number is Z equals 8. Goes 1, 2, 3, 4, 5. Wait. 1, 2, 3, 4, 5, 6, 7, 8. Right?
Volume of the primitive unit cell is half the volume picture of the primitive unit cell. It is useful to express this said and find
Okay, yeah, so it is these corner things. Okay. I'm just looking at the wrong lattice. It is these corner things. So it's 8. Yeah. Okay, just double checking, because I saw this picture. I didn't realize it's an entirely different lattice, so I shouldn't have been looking at that picture anyway. But, you know, I was looking at the picture, okay? You can't knock me for looking at a picture. Okay, it's just a picture. As in 2 dimensions, so Wegener-Seitz cell can be constructed around each lattice point, which encloses all points in space that are closer to that lattice point than to any other point in the lattice, as well. Blah, 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 blah. Note that this cell is bounded by the perpendicular bisecting planes between lattice points. These cells, being primitive, can be stacked together to fill all of space, as shown in 12.14. Yeah. The face-centered cubic FCC lattice. The face-centered FCC lattice is a simple cubic. This is how you study. Now, people like to talk about the Mondo method of studying, whatever it is, you know, that 10 minutes on, 10 minutes off form of studying? No. This is a true method, reading as slow as humanly possible. The face-centered lattice is a simple cubic lattice where there is an additional lattice point. See, my reading is like not great either. It says that I'm tired. I should not have gone to the gym and ran this morning. Should have gotten more sleep. Would have had me in a better condition. Well, anyway, I have to go somewhere at 5, so doesn't even matter anyway. Doesn't even matter anyway. Okay. The face-centered lattice is a simple cubic lattice where there is an additional lattice point in the center of every face of every cube. This is sometimes known as cubic F or face-centered. The unit cell is shown in the left of figure 12.15. A plan view of the unit cell is shown on the right of figure 12.15 with heights labeled to indicate the third dimension. I don't see heights labeled. Where are the heights labeled? I don't get it, but... In this picture, there are 8 lattice points on the corners of the cell, each of which is 1/8 inside of the conventional unit cell and 1 point in the center of each of the 6 faces, each of which is half. Thus, the conventional unit cell contains exactly 4 lattice points. So you got 1 here. These would make up 2, these would make up. So 1, 2, 3, 4. Okay. Yeah. 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 Blom, 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 blom. Yeah, anyway. In this picture, there are 8 lattice points on the corners of the cell. 3, 6, 7, 8. Each of which is 1/8 inside of the conventional unit cell. I don't think each of them is 1/8 inside. Which one are they talking about? I don't. What are they talking about?
Let us consider a face-centered cubic lattice. The conventional unit cell of this lattice is shown here.
Like this
It is a
anyway.
cube with lattice points at the corners and at the centers of all faces. But note that when we say FCC lattice, we mean the points generated by the repetition of this unit cell and not the unit cell itself. A given lattice can be generated by infinitely many different unit cells. The conventional unit cell used for FCC lattice, shown here, is a non-primitive one because it has lattice points other than those at the corners, the face-centering ones. In a primitive unit cell, lattice points will be there only at the corners. For some purposes, for example, to determine the reciprocal lattice, it is useful to describe the lattice with a primitive unit cell. In this video, we describe a primitive unit, one of the primitive unit cells of the FCC lattice. For this, let us construct a vector from this origin to the backface center, shown here as the vector A1. Similarly, we take vector A2 and vector A3 from the same origin to the centers of other faces meeting at that origin. So we have selected one of the corners of the cube.
Oh, I guess this entire thing is a cell, so there is 8 points here, and they are all exactly 1/8 inside. Yeah. Yeah. So there's 4 and then 8, and they're all 1/8 inside, and if you include and 1 point in the center of each of the 6 faces, which is exactly 1/2 inside. Yeah. So 1, 2, 3. 8 times 1/8 is 1. It's 4. Yeah, okay. I get it. The plan view also gets the idea behind, though, because 1, 2, 3, 4. Yes. I get it now. I get it. I understand the picture. Oh, he just describes it in like the worst way, dude. Well, I guess not. I guess in this case, it's my fault. I'll take the L in it. It's not your fault, Simon. Okay, it's me. It's not you, it's me. Okay, thus a conventional unit cell contains exactly blah. Packing together these unit cells to fill space, we see that the lattice points of a full FCC lattice can be described as being points having coordinates x, y, z, where either all 3 coordinates are integers times the lattice constant a, or 2 of the 3 coordinates. Wait, I'm not understanding. Like, I'm not absorbing. Packing together these unit cells to fill space, we see that the lattice points of a full FCC lattice can be described as being points having coordinates x, y, z, where either all 3 coordinates are integers times the lattice constant a, or 2 of the 3 coordinates are half odd integers times the lattice constant a, and the remaining 1 coordinate is an integer times the lattice constant a. What the fuck? Why are you describing this shit like this? Why are you describing a picture in like these terms like I'm blind? You can just draw it. It's sometimes convenient to think of the SCC lattice as a simple cubic lattice with a basis of 4 atoms per conventional unit cell. Like, I don't get how you come up with this. use basis vectors. Face xy, face xz, face yz. Okay, I guess, yeah. I guess, yeah, if you take half integers, so you can take like this whole thing. This is a whole thing. A. If you want to get to these ones in the middle, they're half integers. Yeah, so the corners are defined by that. Yeah, okay. Again, this expresses the points of the lattice as if there were 4 different types of points, but they only look inequivalent because we have chosen a conventional unit cell with 4 lattice points in it. Since the conventional unit cell has 4 lattice points in it, we can think of the FCC lattice as being 4 interpenetrating simple cubic lattices. Again, we can check that this set of points forms a lattice. In terms of our first definition of a lattice, we write the primitive lattice vectors of the FCC lattice as that in units of the lattice constant. Again, it is easy to check that any combination, blah, blah, blah. Blah, 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 and that's because you can take the determinant of it. Top is simple cubic, this is body centered, and this is face centered. Although the simple cubic lattice is conceptually the simplest of all lattices, in fact, real crystals of atoms are rarely simple cubic. To understand why this is so, think of atoms as small spheres that weakly attract each other and therefore try to pack close together. When you assemble spheres into a simple cubic lattice, you find that it is a very inefficient way to pack the spheres together. You are left with a lot of empty space in the center of the unit cells, and this turns out to be energetically unfavorable in most cases. Packing of spheres into simple cubic BCC and FCC lattices are shown in figure 12.18. It is easy to see that the BCC and FCC lattices leave much less open space between the spheres than packing the spheres in a simple cubic lattice. See also exercise 12.4. Correspondingly, BCC and FCC lattices are realized much more frequently in nature than simple cubic, at least in the case of a single atom basis. For example, the elements aluminium, calcium, gold, lead, nickel, copper, and silver. Ag is silver, right? Yeah, I know my periodic table. Okay. What am I getting a notification for? Oh, topic review. I can't make it. So these elements are FCC, whereas the elements lithium, sodium, potassium, iron, MO. What the hell is MO? Bro, what? Bro, what? Why did it do that? I have never seen this element in my life. Morbius? What is this, number 42? Why do I not know this element? Is it a new element? This picture is inaccurate. Electrons do not actually orbit around a pattern like this. They actually exist in probability densities. Because if you actually knew the wave function, then you would realize that this is actually incorrect. Like, I never know how to get it aligned back in the center. How do you do that? Other lattices in 3 dimensions. Cubic. Body centered, face centered. That. Base centered. There's only 14 types. Okay. Damn, that sucks. Okay, while it's an extremely deep fact that there are only 14 lattice types in 3 dimensions, a precise statement of this theorem as well as the proof of it are beyond the scope of this book. The key result is that any crystal, no matter how complicated, has a lattice which is one of these 14 types. Some real crystals. Once we've discussed lattices, we can combine a lattice with a basis to describe any periodic structure, and in particular, we can describe any crystalline structure. Several examples of real and reasonably simple crystal structures are shown. Yep, body-centered. Sodium, pretty simple. Cubic P. Damn, okay. Sodium chloride. Okay, that's pretty cool. Okay. Ugh. Yeah, the plan view makes sense. The plan view is a lot simpler to kind of understand because it's 2-dimensional. It's not 3-dimensional. It's a simple 2-dimensional object that my 2-dimensional brain can understand. Yes. My brain is 2-dimensional. Yes. Yes, my brain is 2-dimensional. Yes. Yes, my brain is 2-dimensional. Yes, my brain is indeed 2-dimensional. I have a 2-dimensional brain. Blah, 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 blah. Ashcroft and Merman. Let's pull up Ashcroft and Merman. is this, chapter 4? Chapter 4 is page 63. Jesus Christ, this book is fucking dense. Damn, it's a shame most of these pages are fucked up. Time to read about the reciprocal lattice. Wait, what were the takeaways? Definition of lattice in 3 different ways. Definition of unit cell. Construction of the Wigner-Seitz unit cell. One can write any periodic structure in terms of a lattice and a basis. In 3D, know the simple cubic lattice, FCC lattice, and the BCC lattices in particular. Orthohombric and tetragon lattices are also very useful now. FCC and BCC lattices can be thought of as simple cubic lattices with a basis. With a basis. What is with a basis? With a basis. With a basis. Where's the basis? Drop the bass. Just double checking my answers. Okay, reciprocal lattice time it is. This is going to be worse. Uh-huh. Okay, so check it out. Why am I so sweaty? I do not know. Okay, I'll be right back. Give me like 10 minutes, brother. Guess who is back? Gonna pack up these beans that I made into the fridge. They go. Boom. Now we got a shit ton of beans. What are we gonna do with beans? I don't know. Well, I do know we're gonna eat them. Okay. I'm just not gonna eat them today. Probably tomorrow. Beans, rice, and fish. That's all we have. And kimchi. And we have carrots, but I'm too lazy to chop them up and prepare them.
Who do not love Shih Tzus? Not only are they adorable, they also have a fascinating history. So let's talk Shih Tzus. Back in ancient Tibet, monks were all about these holy pups called Shih Tzus. They were like mini lions that were believed to bring mad good luck because lions were sacred to Buddhists. They started getting hooked up with Chinese emperors left and right. Fast forward to the Ming Dynasty, and Shih Tzus were living their best life in the royal court. But if you got caught with one without an invite, it was basically game over, like death sentence. Then, when China started trading with the West, they were like, nah, these Shih Tzus are too exclusive for y'all dusty peasants. But when the 20th century hit, things got shaky. The Qing dynasty fell, the royalty crumbled, and sadly, Shih Tzus were left hanging. In 1930, a couple of crafty Brits managed to get a hold of them, and they ended up in England. After a few more made their way over in the next couple of years, these little guys got busy. Those original 14 dogs from China became the founding fathers and mothers of all modern-day Shih Tzus. After World War II, soldiers coming back to the US were like, yo, check out these dope little dogs, and brought Shih Tzus home. Breeding programs kicked off, and everyone was vibing with their unique beauty and chill temperament. The UK were all about the Shih Tzus, recognizing them in 1946, and the American Kennel Club finally gave them the nod in 1969. From that day on, they went from zero to hero, becoming one of the coolest and most popular dog breeds around.
Best in show tonight is a Shih Tzu. where Mark Wahlberg is sitting alone on the couch, and then Ted says, "Holy crap!" And then Mark Wahlberg like rushes in like something incredibly bad just happened, and he goes like, "Well, what's wrong?" And then Ted goes, "I got on the internet for the first time. There's so many, or there's so much, and I think that's supposed to be," he says, "pornography on here, but instead it's breeding announcements for Bully XL pitbulls, Mewtwo X Elsa, Frankenjar's Thriller. Did you see that one?"
Okay, all right, guys. Listen, we can do a little bit of fun. We do a little bit of trolling around this neighborhood. Fuck, this chapter's long. Wow, there's so much opportunity to learn about a brand new topic that I've never learned about before. There's so much knowledge to gain. Isn't that wonderful? See, that's how we gotta think. And that's how we are thinking. Okay. You know what I'm actually going to do? I'm going to take away all of my tags. Actually, I'm just going to say study physics. And let's see if that helps. Because I think those tags are actually ruining my viewership. But anyway. In the last chapter, we explored lattices and crystal structure. However, as we saw in chapters 9 through 11, the important physics of waves and solids, whether they are vibrational waves or electron waves, is best described in reciprocal space. Could I live monitor what's going on here? Let's see. Monitor and output. Oh no. It's an X. Whoa. That's kind of good. Yeah. Whoa. Okay, monitor off. I don't think I can monitor my output. Well, it's whatever. Anyway, this chapter thus introduces reciprocal space in 3 dimensions. As with the previous chapter, there is some tricky geometry in this chapter, and a few definitions to learn as well. As a result, this material is a bit tough to slog through, but stick with it because soon we will make substantial use of what we learn here. At the end of this chapter, we will finally have enough definitions to describe the dispersions of phonons and electrons in 3-dimensional systems. Alright, time to read this. Should I read this or should I just take a break? Should I play a little bit of Call of Duty? Should I read this or should I play a little bit of Call of Duty? I'm wondering. Dude, I would much rather just read this. Because apparently this is just better. I feel like this would be easier to understand, man. Okay, anyway, let's just start reading. You don't know until you just read. So let's just read. Shall we? Let us first recall some results from our study of one dimension. We consider a simple lattice in one dimension Rn equals Na with n an integer. Recall that 2 points in K space. Let me see actually the okay, I'm spending so much time like reading, trying to figure out what I can skip, that in the time that I spent trying to figure out what I can skip, I could just do it. So let's do it. Let's read this. However far we get in an hour is how far we get. I don't think we'll be able to finish this in an hour, but... Okay, let us recall some results from our study of one dimension. We consider a simple lattice in one dimension Rn equals Na with n an integer. Recall that 2 points in K space. Actually, something just came up in my mind. I should check this. Wrong course. Okay, let's just read this. Let's first recall some of our results from our study of one dimension. We consider a simple lattice in one dimension Rn equals Na with n an integer. Recall that 2 points in K space were defined to be equivalent to each other if K1 equals K2 plus Gm, where Gm equals 2 pi m over A with m an integer. The points GM form the reciprocal lattice. Yes. Recall that the reason that we identified different k values with each other was because we were considering waves of the form e to the ikxn equals e to the ikna with n an integer. Because of this form of the wave, we find that shifting k to k plus gm leaves this functional form unchanged, since e to the ik plus gm equals e to the ik plus gm na equals e to the ikna e to the I 2 pi m over a and a, which is equals to a to the I kxn. Yeah, because the NA's cancel out. And since GM equals... Yeah, we use that this equals 1. Yeah, because the A's cancel out. Why are you able to say that equals 1? Oh, Euler's identity. Okay. Totally forgot about that. That e to the ix can be written as cosine of x plus I sine of x. Damn, there's so much fundamental laws and truths and beauty in the world. There is so much fundamental beauty in the world. Cheers to that. Generalizing this one-dimensional result, we define that given a direct lattice of points R, a point G is a point in the reciprocal lattice if and only if e to the I g dot R equals 1. To construct the reciprocal lattice, let us first write the points of the direct lattice in the form. Here we specialize for the three-dimensional case, with n1 and n2 and n3 integers, and a1, a2, a3 being primitive lattice vectors of the direct lattice. We now make two claims. We claim that the reciprocal lattice is a lattice in reciprocal space. Okay. We claim that the primitive lattice vectors of the reciprocal lattice, which we call b1, b2, and b3, are defined to have the following property: that they are equal to 2 pi delta ij. Yeah. B1 equals 2 pi A2 times A3 over A1 times A2 times A3. A1 dotted with B1 equals 2 pi. A2 dotted with B1 equals 0 because they're orthogonal. We want to find a vector b1 such that b1 dot a1 equals 2 pi and b1 dot a2 equals b1 dot a3 equals 0. The vector b1 can be found by taking the cross product of a2 and a3, which gives a vector perpendicular to both a2 and a3, thus satisfying the dot product being 0. To also satisfy b1 dot a1 equals 2 pi, we normalize this cross product by dividing the volume of the parallel pipeds spanned a1, a2, and a3, which is a1 dot a2 cross a3, and multiply by 2 pi to meet the Kronecker delta condition. Cross product of a2, a3. Does it get the direction, I guess? And then normalizing it, okay. Or this gives a perpendicular vector. And you normalize it, okay. Claim that these are in fact the primitive lattice vectors for the reciprocal lattice. To prove this, let us write an arbitrary point in the reciprocal space as that. And for the moment, let us not require m1, m2, and m3 to be integers. We're about to discover that for g to be a point of the reciprocal lattice, they must be integers, but this is what we want to prove. Okay. Also, like, I like how they go into such detail about doing this step by step, but then for this, they just kind of do it. It's so weird what things they decide to, like, specifically go into and what things they don't. It's really odd, but anyway. To find points of the reciprocal lattice, we must show that equation 13.1 is satisfied for all points R of the direct lattice. We thus write e to the I g dot r. It's going to be that times that. Just going to be 2 pi I. Yeah, because a1 dot b1 is going to be 2 pi. Yeah, b1 dot a1 is going to be 2 pi. Because they're in the same place, and then 2 pi, and then you get all of these. In order for G to be a point of the reciprocal lattice, this must equal unity for all points R of the direct lattice, i.e. for all integer values of n1, n2, n3. Clearly, this can only be true if m1, m2, and m3 are also integers. Thus, we find that the points of the reciprocal lattice are precisely those of the form equation 13.4 with m1, m2, and m3 integers. This further proves our claim that the reciprocal lattice is, in fact, a lattice. Great. The reciprocal lattice is a Fourier transform. I'm going to skip this, because I don't think we need to Fourier transform shit in this class. I don't think so. I hope not. At least in discussion, we didn't have to Fourier transform anything. We just started off from some, some wave functions.
This person that she saw on the Disney cruise, 80% of the cup, Diet Coke, slid it over to the regular Coke, filled up the last 20% with regular Coke. She said, this guy's an innovator. And then I got to thinking, you know what they need? If they're going to keep making dog shit Coke freestyle machines that like barely work with antiquated touchscreen technology, there should be a Coke machine that is just a dial, and the dial goes from like 0 to 100. And you can choose what percentage of a real Coke you want. Like some, you could be like, dude, I don't want a Coke Zero. Like I've been walking a lot today. Give me like a Coke 32. And then I realized, you know what the problem is? There's gonna be some motherfucker at the machine who's gonna be working at like the gas pump, and they're gonna be like, they want Coke 27, but they're gonna hit like 28, and then turn the dial and go like 26, and then 28, and then 26. Then they're gonna get to 27, but they've been twisting it so much, they're like, I don't know, 28. Oh, I had it. Well, I was on autopilot. 26, and they're gonna be waiting there like, brother. It's an eighth of a gram of sugar difference, bro. You can't possibly tell the difference. I love it though. I can feel myself. Like how fun it would be that it wouldn't be like a little dial too. Like it wouldn't be like an old stereo dial. It'd be like a fucking like a bank vault dial. It'd be like it wouldn't be some digital no haptic feedback piece of crap. Okay? And the most annoying guy you ever met would be like, bro, you can tell the difference. Coke 39 is the best Coke. Yeah, Coke 38 is pretty good. Coke 40 is a little rich for me, but Coke 39? No! Coke 39 goes crazy. This person that she...
That's so funny. Okay. Okay. That's enough. That's enough. Northern Line is really funny, dude. God damn. Can you imagine if he was doing his types of bits and shticks? Oh, I just realized there's like a little shadow that shows up between the windows. It's pretty clever. Whoever designed that must be like, I am the genius. I am the unappreciated genius. I am the stone that the builder refused. I am the visual, the inspiration. Okay, anyway. Reciprocal lattice points as families of lattice planes. Another way to understand the reciprocal lattice is via families of lattice planes of the direct lattice. A lattice plane or crystal plane is a plane containing at least 3 non-collinear and therefore an infinite number of points of a lattice. A family of lattice planes is an infinite set of equally separated parallel lattice planes which taken together contain all points of the lattice. So a lattice plane is a plane containing at least 3 non-collinear and therefore an infinite number of points of a lattice. At least 3, so the 1, the 2, and then the 3. In figure 13.1, several examples of families of lattice planes are shown. Note that the planes are parallel and equally spaced, and every point of the lattice is included in exactly one lattice plane. I now make the following claim. The families of lattice planes are in one-to-one correspondence with the possible directions, so they're bijective. The families of lattice planes are in one-to-one correspondence with the possible directions of reciprocal lattice vectors to which they are normal. Further, the spacing between these lattice planes is d equals 2 pi over g minimum, where g minimum is the minimum length of the reciprocal lattice. This correspondence is made as follows. First, we consider the set of planes defined by points r, such that for some integer m, g dot r is equal to 2 pi m. This defines an infinite set Explain this. Okay. Like, how it's criminal to be able to do this and not, like, define your axes, dude. It is fucking criminal. It's criminal, it's criminal, it's criminal, it's criminal. It's criminal, but whatever. This defines an infinite set of parallel planes normal to G. Since e to the I g dot r equals 1, we know that every lattice point is a member of one of these planes. However, for the planes defined by equation 13.7, not every plane needs to contain a lattice point. So generally, this is a family of parallel equally spaced planes, but not a family of lattice planes. For this larger family of planes, the spacing between planes is given by distance equals 2 pi over G. To prove this, we simply note from equation 13.7 that two adjacent planes must have g dot r1 minus r2 equals 2 pi. known as Miller indices. One first chooses edge vectors. What about gooning vectors? One first chooses edge vectors. AI for a unit cell in direct space, which may be primitive or non-primitive. One then constructs reciprocal space vectors bi to satisfy ai.bj equals 2 pi delta ij. In terms of these vectors bi, one writes hkl or hkl with integers hkl to mean the reciprocal space vector. Reciprocal space vector. Note that Miller indices can be negative. Okay, I really don't want to read this anymore. So instead of half-ass reading it, instead, I'm going to pause it here and I'm just going to call it. I'm going to call it. I'm going to call it. Peace.